Hello there, Nareg is here. Today I'm gonna solve the third exercise from second session 2013 chemistry, which is an exercise related to electrochemistry. So let's start. Zinc copper ZnCu galvanic cell. The oxidation reduction reaction is a galvanic cell. In a galvanic cell is a spontaneous reaction that produces electrical energy. The electrical energy is produced when the oxidation and reduction half reaction take place in separate containers, joined by an apparatus that allows electrons to flow. Zinc metal has tendency to lose electrons more than copper metal. 4 attempts have been done to construct ZnCu galvanic cell. Each of the schemas shown below represents an attempt for constructing this cell. In the first one, we have the schema 1. We have Zu strip of copper, which is dipped in Cu2+, that's great. The strip of zinc is dipped in Zn2+ solution, that is great also. We have a salt bridge, but the switch is open, so the lamp will not light, will not function. The schema number 2, we have Zn stripped immersed in Cu2+. So this is again another reason that cell will not function. Cu is immersed in Zn2+. Again, that's another way of saying that this galvanic cell will not function even if the switch is closed. A third one, we have Cu in Cu2+, Zn in Zn2+, switch is off, but instead of salt bridge we have a wire, so copper wire. That's why again we do not have a salt bridge. Again, the lamp will not function. As for schema number 4, we have Cu in Cu2+, Zn in Zn2+. The salt bridge is functioning normally. We have a salt bridge and the switch is off. Switch is closed. The lamp will function. Justify why the lamp does not light in each of the 3 attempts for constructing the ZnCu galvanic cell as shown in the schema 1, 2, and 3. So we already said previously, in the first one the switch is open, the second one we do not have Zn in Zn2+, Cu in Cu2+. The third one we have copper wire, which should be salt bridge, and of course the fourth one is the functioning cell. In attempt 4, as shown in schema 4, the lamp lights indicating that the galvanic cell is operating. Indicate the direction of the electrons flow in the ZnCu galvanic cell. So, in the text they already said that Zn has a greater tendency to lose electrons than Cu, so it will be the one who is losing electrons. So the electrons will flow from Zn. They will flow from Zn towards Cu. So this is how you have the flow of electrons. Write the half reaction that takes place at the anode and the half reaction that takes place at the cathode. So at the anode we have an oxidation, which can be written as Zn, gives you Zn2+ plus 2 electrons. As for the cathode, we have a reduction which is taking place, and in this case it's Cu2+ plus 2 electrons. It gives you Cu. Now deduce the overall reaction, the equation of the overall reaction. So in order to make the overall reaction you simply have to add them. Zn plus Cu2 plus, it gives you Zn2 plus Cu. Alright. Explain why the nitrate ions NO3- of the jellified electrolyte in the salt bridge move towards the anode half cell as shown in schema 4. Now, in the anodic part, we have already oxidation where Zn solid is generating and being transformed to Zn2 plus ion. So the positive charges are increasing in the half anodic cell. We need negative charges to balance this variation of charges. So NO3- will migrate towards this anodic part. Give the written cell representation of the operating Zn Cu cell galvanic cell. So you simply have to say that it is Zn2 plus, salt bridge, and then Cu2 plus Cu. Take out from the text the information which tells how electrical energy is produced in a galvanic cell. So it is produced when the oxidation and reduction reaction takes place in separate containers. This is how you're gonna have the electrical energy formed in this case. That was all for this exercise. This was exercise number 3 from second session 2013. I hope it was helpful, so I'm gonna ask you to subscribe to my channel. You'll be notified whenever I upload new material, new videos. I can also share with you my Instagram and Facebook account. You can contact me directly or simply leave a comment below. That's all for this time, and see you later.